Hello everyone. I was just told that I should introduce myself. So my name is Francesc Sánchez. I'm coming from Barcelona. I studied civil engineering there. Then I did my master's in Milano. And I started working in a small company building unitized system and curtain walling. And then I jumped to Bellapart, where I've been for 4 years now, working in singular projects as the one we'll see today. This presentation is focused on the Louvre Saint Honoré project and its new glass canopy in Paris, right next to the Louvre Museum. So, first of all, a little context about Bellapart, for those who might not know us. We're a company based in Olot, in the northeastern part of Spain, close to the border with France. And we specialize in building steel and glass structures with a focus on, well, as you can see here, singular projects. We have more than 80 years of experience worldwide, but mostly in the French market and also the UK and the United States. So now to the project that we'll see today. This is the Louvre Saint Honoré project, which is this building that you see in red. Which is next to the Louvre Museum in the center of Paris. And this project consisted in the renovation of the facade at the ground level. The architects for this project were Ateliers Jean Nouvel, and with the aid of Tess, Ateliers Jean as the facade consultants. So, as I said, the project consisting in the renovation of the facade at the ground floors. And this project strikes us for the diversity of constructive solution. You can see here the first picture, the fixed modules, which are built as a single glass, an insulating glass unit with a hidden frame to give the appearance of an all-glass facade. Then we have also swing doors which were built at Bellapart and were tested to meet the RC3 anti-burglary resistance classification. Some of them included also windows at the first level to give access to the firefighters in case of an emergency. And you'll see this on the next slide, but behind those windows there's a glass floor. And finally there were some sliding doors which were designed to have the same appearance as the fixed modules, so that when they were closed you cannot tell them apart. You can see somewhere here we had 37 different models with over 2,500 square meters of glazed facade. And in top of the renovation of all these modules, we installed a new glass canopy, which we will see now in detail. This glass canopy spans for over 140 meters along the Rue Saint Honoré and has almost 500 square meters of glazed surface. So, this glass canopy is composed of 84 laminated glass panels, each one of them with 10 millimeters heat strengthened glass, laminated with 1.5 millimeters of sentry glass, with variable width and a height of 3.5 meters. These glass panels are supported by a stainless steel structure divided in 3 components. The top part we have the transom with the brackets that connect it to the building. Then we have the gutter to collect the rainwater. And we have the lower struts at the bottom, again to give support to the glass panels. So now the question is, amongst all the elements that we've seen, why did we choose that to focus on? Well, it has 2 peculiarities that are not apparent. You can see them if you don't know that, which are that the static scheme we use, it's not a traditional one. So the glass panel is supporting the weight of the lower structure and not the other way around. So we're using the glass as a structural element. And then we have the drainage system, which we are using the same struts and give support to the panel against horizontal loads, are used simultaneously as supporting structure and the drainage system, so the rainwater flows through them. So let's start with the static scheme that we adopted. You can see here the elevation of the glass panels. There's nothing particular here. What's particular, and I should move there, it's at the vertical section. You see at the top part the transom with the brackets rigidly fixed to the building with a hinge at the connection of the glass. Again, nothing particular here. But at the bottom, you'll see that the lower struts are hinged at both ends. This means that these struts are not stable in themselves, so we need the glass panel to hold their weight. So, how did we actually build that? You see at the top part, the transom with the brackets which were welded to it and rigidly connected to the structure. To connect the glass panels to the transom, we used standard point fittings. You can find them in the market. No, there was nothing special there. And the particularity is here with the lower struts. You can see a little small there the anchor to the main building, to the column, which has two bolts which are aligned, allowing for the rotation at this point. And also here at the end, with the connection to the glass panel, we used a single bolt, again allowing for the rotation at this point. So, as you can see, we need to put some temporary supports here and here to hold the weight of these elements until the glass panel was installed. Now, for the other particularity, the drainage systems that we used, you can see here a picture during the installation of the glass panels, just before we installed the gutter. You can see at this point here, a small hole that it's only there, it's not at the other connection points. This means that we're using this particular strut to evacuate the rainwater falling onto the glass canopy. So once we install the gutter would have another hole in the same position, and we would install this filter so that the water will be collected by the gutter and then passing through this filter, and through the interior of these round stainless steel tubes to the drainage system of the whole building. So we have the second peculiarity here, that the lower structure is functioning again both as structure and as a drainage system. So given the peculiarities of this project, we need to undergo an ATEX procedure in France. So we run all our numerical analysis. We need to verify all the elements, obviously. So we started with the global model, finite element model, including the glass panels, stainless steel structure, the connections, and so on. This global model allowed us to identify the most loaded glass panels, the most critical points, which were, of course, the stress concentration around the holes and the cutouts to fix the glass panels to the structure, and also the cutouts to fix the gutter to the lower struts. So once we identified these points, we could run some more detailed models. You can see here, in this case, we use Mapla software, which allowed us to properly model the glass panels and the interlayer with the properties, the dependence on temperature, and so on. So we detected, again, the stress concentrations around the holes. They were fine for our calculations, so we were pretty confident with it. But then we needed to validate all this numerical analysis, this finite element analysis, with real-size tests, which is what we're seeing now. We did a series of tests, including the glass panels, the fixations, and so on. And this presentation, we only see two of them, which are the most relevant ones. First one is the one you're seeing. It's a wind load resistant test. So for this test, we took the biggest glass panel we assembled using the transom, the gutter, the connections that were used for the project, and we mounted it in a steel frame to create a pressure box. This steel frame was then sent to the CSTV facilities where the test took place, and was mounted on a wall with an industrial blower. All the seals were joined so that we could apply the wind pressure and suction and validate our results. This this test was carried out in 5 stages. First one, we validated the deflections. So we applied the load both in pressure and in suction at serviceability limit state. Then we increased the load to the ultimate limit state value, and we applied both statically and dynamically with 20 cycles. We then increased the load to 2.7 times the characteristic load, and we checked that there was no breakage and everything worked fine. And finally, as you can see on the right-hand side, we increased the load until the system collapsed. In this case, it was the glass who broke. It broke in bending, and the load that caused this breakage was around 5.1 kilopascals, which was almost 3 times the design load that we had at ultimate limit state. So we were pretty happy with the results. The second big test that we did, this time we did at our facilities in Bellapart. We took a glass panel, we installed, simulating the structure that we would have on site with the top transom, the lower struts, and you cannot see it here because it's removed after the test, but there was the gutter as well. And we did an impact test to see how these glass panels would behave. So the impact test was made with a 50 kilo sandbag, dropped at the bottom part, which is the cantilevered area. And as you can clearly see, the glass broke. But the combination of using heat-strengthened glass and central layer lamination provided it enough residual strength so that the glass would hold. You cannot appreciate here in the figure, but it was pretty rigid, even after breaking. What's interesting to see here is to analyze the breakage pattern. You'll see at the right-hand side that the breaking starts at the corner of the cutout, which is a clear stress concentration point, and was also a thing that we already expected from the analysis. But again, we were pretty happy with the results. And so you can see the result. The installation of these elements has finished earlier this year. And well, we are pretty happy with the result. So we've had a huge project. The installation for this began on 2022. So it's been 3 years that we've been working on this project. And well, we've had the chance to participate in the design and construction of this unique design. As we already said, there's the glass panels, which are not used merely as an infill panel, but as part of the structure. And then there's this unique design for the drainage system. So it's been a nice project. We think that the result is quite stunning, and we had the chance also to validate and contrast the calculations that we do for all projects with real size tests, which is not always the case. So we're pretty happy with that. And that will be all for my part. I would invite you, if you ever go to Paris, to have a walk around. It's in the center. It's very nice. And well, that's all. I have some time left, so if anyone has any questions, I'll be happy to answer them.